This resource is the third in a four-part series on factoring polynomials. Part 1 considers the greatest common factor. The GCF is defined. We present a method for factoring the GCF out of a polynomial and provide examples. Part 2 considers factoring a trinomial into a product of two binomials when the coefficient of the x squared term is 1. We present the general process and look at multiple examples. Part 3 considers certain special cases. Those cases are defined, then examples are provided. Part 4 looks at factoring a trinomial into a product of two binomials when the coefficient of the x squared term is not 1. We look at the general process, then multiple examples. Some polynomials have special forms. These forms include the difference of perfect squares, a perfect square, the difference of perfect cubes, or the sum of perfect cubes. Each of these types of polynomial can be factored easily to a specific format. Let's look at the first type, the difference of perfect squares. A perfect square is a number or variable expression that results from multiplying something by itself. For example, 25 is a perfect square because 25 equals 5 squared, or 5 times 5. How does this help us? A polynomial is a difference of perfect squares if the terms are perfect squares and they are being subtracted. In general, this means you have a squared minus b squared. Polynomials of this form can be factored as a product of two binomials, where you have a plus b times a minus b. When factoring, you want to identify what exactly is being squared to give the perfect squares, then substitute into the general factored format. Let's look at some examples. Suppose you want to factor x squared minus 9. First, recognize that x squared is x squared, and that 9 is 3 squared. So x squared minus 9 is factored as x plus 3 times x minus 3. What if we want to factor 4x squared minus 25? 4x squared is the quantity 2x squared, and 25 is 5 squared. So 4x squared minus 25 is 2x plus 5 times 2x minus 5. What if we have x to the fourth power minus 49y squared? X to the fourth is x squared squared, and 49y squared is the quantity 7y squared. When we factor, we get x squared plus 7y times x squared minus 7y. Now let's look at another special form, a polynomial that is a perfect square. Perfect squares are not as easy to recognize as the difference of perfect squares. These polynomials will have three terms, of which the first and last terms will be perfect squares. The middle term will be 2 times the product of what was being squared in the first and last terms. In general, if you have a squared plus 2 times a times b plus b squared, you can factor that as a plus b times a plus b, or a plus b, the quantity squared. The process for factoring a perfect square is a little more complicated than that for difference of squares. We will start the same way, by identifying the first and last terms as perfect squares. Then verify that the middle term is twice the product of the square roots of the first and last terms. Finish by substituting into the general format. Examples will help make sense of this process. Suppose you want to factor x squared plus 22x plus 121. We start by realizing x squared is x squared, and 121 is 11 squared. Now we verify that the middle term equals 2 times what is being squared to form the first and last term. Because 22x does equal 2 times 11 times x, we know we have a perfect square to factor. So x squared plus 22x plus 121 factors as the quantity x plus 11 squared. But how does this process work with a minus sign in front of the second term? Let's find out. Suppose we want to factor x squared minus 10x plus 25. X squared still equals x squared, and 25 is 5 squared. But 25 could also be factored as negative 5 squared. We verify that 10x does equal 2 multiplied by 5 multiplied by x. Because we had minus 10x, we use the minus 5 option. So the factored form will be the quantity x minus 5 squared. But what if we had two terms, but they are cubed instead of squared? Perfect cubes work the same way as perfect squares, except the number is multiplied by itself 3 times. For example, 8 is a perfect cube, because it equals 2 times 2 times 2. The formats for factoring the sum or a difference of perfect cubes are very similar. The first set of parentheses is what you started with, just without the cubes. The first term of the second set of parentheses drops the power to squared. Then you switch the sign and write the product of the things being cubed. Then the last term is always plus the second term of the original polynomial, but squared. The process for factoring the sum or difference of perfect cubes is very similar to factoring the difference of perfect squares. Determine what is being cubed, then fill in the parentheses according to the factor format. Let's look at some examples. Suppose we want to factor x cubed plus 125. We recognize x cubed as x cubed and 125 as 5 cubed. This means we have x cubed plus 5 cubed. Knowing this, we can substitute into the generic factor format. We have x plus 5 times x squared minus 5 times x plus 5 squared. We have to remember to switch the plus to a minus in front of the second term. Simplifying, we are left with x plus 5 times x squared minus 5x plus 25. What if we want to factor 27x cubed minus 343? 27x cubed is 3x cubed. 343 is 7 cubed. So we have 3x cubed minus 7 cubed. Plugging into the general format, we have 3x minus 7 in the first set of parentheses, and 3x squared plus 3x times 7 plus 7 squared in the second set of parentheses. Simplifying, we are left with 3x minus 7 times 9x squared plus 21x plus 49. The key to using these special forms is to be able to recognize perfect squares or perfect cubes. Once you can recognize these special types of numbers, these special forms give you a nice shortcut to make your factoring life easier. If you cannot recognize the special form right away, the difference of perfect squares and the perfect square formats can both be factored using the method for factoring described in the previous edition of this factoring series. But what happens if you have a trinomial quadratic where the leading coefficient, the a, is not 1? Stay tuned for the next resource in the series.